That's on Saturday. And then you have quiz 5, which covers 5-1, 5-5, and 5-6, are due on Sunday. Reminder that Pearson again sent a second email to me that they're going to have maintenance next Thursday, Friday. So just to keep that in mind. Today we're going to talk about the complex zeros. Before I go to the handout that I emailed out earlier in the week, I want to make sure you understand, believe it or not, the number system so that this section makes more sense to us. So way back in grade school, and you don't need to copy this down, it's just something to have in the back of our mind. Way back in grade school, you talked about a set of numbers, and you called that set of numbers the natural numbers, and we call it N for natural numbers. And that's the set of numbers that you count by. So if you're counting people in a room, start with 1, 2, 3, 4, and so forth. So that's a set of natural numbers. And then you add in 0, and you get a set of something called the whole numbers. So whole numbers basically on the number line start at 0 and then include the natural numbers. So it's 0, 1, 2, 3, 4. So as examples, 1, 2, 3, and this adds in 0. Then once you get a little further along your math track, you add in the negative numbers, and you call that the set of integers. So the integers are literally what you would mark on a number line going to the left and to the right of 0. And then once you get into middle school, they add in what we call the set of rational numbers. And the set of rational numbers includes your fractions and decimals that are repeating or terminating. So pi is not in there yet. E is not in there yet, but it's a set of rational numbers. And then sitting over here someplace is a set of irrational numbers. And that includes pi, E. So it's all the fractions and decimals that do not terminate and do not end. And if you add all of those guys together, right now you have the set of real numbers. Okay, and that's what we've been dealing with. So when we talked about zeros yesterday, we were talking about the zeros that fit within this set of number systems. Now sitting over here all by itself are the i's. So 2i, 3i, 4i, and this is what we're going to add in today. And then when we add both of those guys together, so the set of real numbers and the set of i's, you end up with a set called the complex numbers. And that's as big as our number system allows us to go. That's it. That's everything. So again, yesterday when we found our zeros, we were stuck in this set of real numbers. Today we're going to add in the imaginary solutions and end up with what we call our complex zeros. So recognize that real numbers are complex numbers. So when we were finding the zeros yesterday, we were finding some of the complex zeros. We just weren't finding all of them, which is why we'll add in the I today. So and for some reason, people really have a hard time understanding that real numbers are part of the complex number system. So what we've been doing is working our way out in terms of a smaller group, getting to a bigger group, and so forth. Okay, so the front page of the handout, if you printed it out, does kind of go through that. So it gives you a list of numbers, and the list of numbers are -1, 0, square root of 2, 3/2, 5, and 3i. And then the question asks, which of the following numbers in the list above are complex numbers? Well, they're all complex numbers. These guys, the first ones, are what we consider to be real numbers. This one all by itself is an imaginary number, which are really important for the engineering people. Doesn't matter for my vet or the sciences, but for engineering, you need those imaginary numbers. And then when we combine them together, again, you get the set of complex numbers. So all of those listed above are complex numbers. So just trying to reiterate, to backtrack just a little bit, the square root of 2 is the only irrational number in that list because it involves a radical. It's usually a non-terminating decimal then. So the definitions, there's a bunch of definitions. I'm going to really go through them at a pretty quick pace because it's just definitions in a mathematical speaking that we really don't need for us. So a complex polynomial is the same thing we've been dealing with. It's our polynomial. The coefficients can be complex numbers. That's okay because all our coefficients have been, you know, nice integer values stick with the integers. Those are complex numbers. The fundamental theorem of algebra reiterates what we said yesterday. So if you have a complex polynomial, same thing we had yesterday, then you have complex zeros, which is okay. The polynomial function has a degree of n, then we know it has one complex zeros, and that complex zero can be our r again, or our c as we called it on the first day, and you can factor it. So those theorems are simply telling us we can factor our polynomials. And if you do factor it, the theorem on the box that's next down on the page simply tells you that if you have a complex polynomial, again, the word complex here is meaningless. It's the same thing we were doing yesterday. They're simply saying that all of a sudden those coefficients can be complex numbers, but we know that in terms of the overall number of zeros, so we're going to drop off the word real, the number of zeros altogether is the highest degree n. So again, the exponent lets us predict how many zeros we're looking for. Okay, so let's do a really quick example. I know I flew through all that theorem in math speak because it does not really impact us anywhere. But let's do a complex function. Let's do x squared plus 9. And again, you should say, well, that looks exactly like what we've already been dealing with. And it is. All that's changing is we're recognizing that now those coefficients and constants are complex numbers, not just real numbers. Well, if we went to solve that, we already know how to solve it. We'd end up square rooting both sides. And what we're going to end up with are imaginary solutions. So x is equal to plus or minus the square root of -9, which is 3i. So the two solutions, because it was a second degree polynomial, are 3i and a -3i. What's important about this is we have to recognize that these are complex pairs or complex conjugates. And that's what's at the bottom of the first page. Sorry, I had to plug it in again. So conjugate pair theorem says if you have a polynomial whose coefficients are real numbers, and if r equals a plus bi is a 0, then a minus bi is also a 0. They have to occur in conjugate pairs. And a conjugate pair simply means the sign on the imaginary part is opposite. The sign on the real part doesn't change, but the sign on the imaginary part is opposite. We know this because every time we use the quadratic formula and we end up in the complex world, we always end up with a plus or minus in front of that radical, and that's where that complex pair is coming from. So we're just recognizing that they occur as conjugate pairs. And we already knew it, we just hadn't formally stated it yet. So on the homework, literally, that's all the theory we need. On the homework, it's going to start off with problems that look like this. So this is example 1. So information is given about a polynomial whose coefficients are real numbers. We want to find the remaining zeros. So for part A, it's going to tell me that it's a degree 3 and that the zeros are 4 and 3 plus I. So again, all they're asking for is information is given. We want to find the remaining zeros. Well, because it's a degree 3, we know we have to have 3 zeros. But they only gave me 2 zeros. They gave me 4, and they gave me 3 plus I. So the remaining 0 has to be the conjugate pair to the I one that is given. So the remaining 0 is 3 minus I, and that's it. That's all there is to the question. That's all they're looking for. It's my kind of question. No work involved. All you have to do is write it out. So same thing. This time, let's say it's a degree of 4. And the zeros are 2 minus I and a negative I. Well, if it's a degree of 4, it must have 4 zeros. So the remaining zeros have to be the conjugate pairs. So for 2 minus I, we would have 2 plus I. And from the negative I, its conjugate would be a positive I. So again, only the sign on the I is changing. And that's it. You found the remaining zeros. So that's the beginning of your homework. Any questions or comments about that?
Okay.
Makes sense? Okay, example 2, a little more complicated, asks us to form a polynomial. So they actually want me to come up with a polynomial function. With real coefficients, it's degree 4. And as the zeros, we have 3 with a multiplicity of 2. And then the other 0 that they're giving me is 4i. Okay, let's wait our way through that one. So this time, because we're actually trying to write the polynomial, we need to call it something. We're going to call it f of x. We know that 3 appears as a 0. Well, that comes from a factor of x minus 3. And because its multiplicity is 2, I know to put a square up there. Okay, then I know that we've got 4i as a 0. When I go to write it as a factor, I'm going to switch its sign and make it a negative 4i. So that's this 4i coming in. But right now we've only got a degree of 3. We've got an x squared times another x. And we need a degree of 4. So we have to account for the conjugate. So we're going to come in and write an x plus a 4i. So again, the conjugate pair to the 4i would be a negative 4i. And when I bring it back in as a factor and write it with an x, I switch its sign. Unfortunately, I had the sneaking suspicion that on the online homework, you cannot stop here. You have to FOIL it all out, which I think is a little weird, but what I'm going to do to FOIL it out is actually work with the conjugate pair first, and you'll see why here in just a second. So let's go ahead and FOIL the last two together. That'll give me an x squared. I'll get a positive 4ix from the outside, and from the inside, I'm going to get a negative 4ix. The last two terms multiplied together, the negative times the positive is a negative. 4 times 4 is 16, and I times I is I squared. Well, that looks ugly. But recognize that the 4ix and the negative 4ix are going to cancel, so those terms are gone. And don't forget, a long time ago, you learned that I squared is defined to be a negative 1. So that's going to take this I squared out and rewrite that as x squared plus 16. So x squared plus 16. So what we've done so far is we've given it real coefficients. In other words, we got rid of all the i's. So in a classroom, this is where I would normally stop. But because that online homework's a little nitpickier about things, we still have to FOIL all this out. So, and you only have one of these. We're going to square first. So I'm going to take that x plus 3 and FOIL it out. That would be x squared plus 6x plus 9. And then we need to multiply that by x squared plus 16. So we're getting there. That's why you only have one of them. What I'm going to do is distribute. So I'm going to take the x squared that's on the second set of parentheses and distribute it into all of these, and then I'll do the same thing with the 16. So x squared times x squared is x to the 4th. X squared times 6x is 6x cubed. The x squared times the 9 is going to give me a 9x squared. That's the x squared times each of the terms in the 3 one. Now we're going to multiply the 16 in. So 16 times x squared gives me a 16x squared. 16 times 6 is 96, I think. That's a 96x. And then 16 times 9, 514. Boy, I'm not checking my arithmetic. Let's double check that to make sure. 16 times 9, 144. Yeah, I knew that one didn't feel good. Okay, and then 16 times 6 is 96. Got that one right. Okay, and then all we have to do is collect like terms and call it good. We will put it in descending order as we're doing it. So we have x to the 4th, 6x cubed. Now we can add the 9 and the 16 together to give me 25x squared plus 96x plus 144. And I did not put one of these on the next exam. And you only have one that's on the homework. So again, if we were in class, I'd have you stop right here. This is not a college algebra kind of problem in terms of skills. So, okay. Whew. So they gave me information about the zeros. They want to know what the other zeros are. And then they gave me information about the zeros and asked me to write the polynomial. So, and now we're going to finally come in and start solving them. So there's no new theory on the solving. It's the same as yesterday. The only difference is now we're going to go find all the i's. So, and at this point, it's just a matter of getting practice. So example 3 tells us to find the complex zeros of the polynomial function f of x equals x to the third plus 13x squared plus 57x plus 85. So x cubed plus 13x squared plus 57x plus 85. So I'm going to find all the zeros and then write f in factored form. So this goes right back to where we were yesterday at the end of the class. So each of my steps, the very first step, we know that we have 3 zeros, and that comes from the highest degree we see. Step 2 is to go do that P over Q list. That's all factors of 85. Not as bad as you think. So plus or minus 1. 2 won't go into it. Does 3 go into 85? 85 divided by 3. No. 85 divided by 5. Yeah, so 5 goes into it. 10 doesn't, I'm sorry, 6 doesn't, 7 doesn't, 8 doesn't, 9, no, 10, no, 11, no, 12, no. I'm going to go all the way up to 17 and then 85. So it's not a really big list, even though 85 is a big number. It's not a very big list. That would be over Q, but Q is equal to 1, so I don't need to rewrite my list. Okay, and then do you remember what would be the next step? What did we do next yesterday? Do I remember?
Graph?
Yep. So step 3 is to graph it. Exactly it. So we'll go graph it. Hopefully you have your calculators with you. If not, go find it. Third. 13x squared. Plus 85. And so my graph looks something like this. So it does look somewhat like we expect it to do. It's an odd degree polynomial, so it starts below and ends above. From our picture, what number should we try in our synthetic division? So this is step 4. What number should we try?
-5.
Yep, we're going to go try -5. So I've got a 1, a 13, 57, and 85. Okay, and before I actually do that, I want to point out something. The graph is giving me the real zeros. We know that we have to have 3 altogether, so only one of them is real. That picture is telling me that the other 2 are going to be complex numbers. They're going to involve I, and the only way we're going to find those is off the quadratic formula. So I know I got to plan a train that I'm driving kind of thing. So bring down the 1, multiplying gives me a -5, adding is 8, multiplying is a -40, adding is 17, and -5 times 17 is a -85, and we get our 0. So again, that's our proof that it's a 0. Good. Okay, what's left down here is our quadratic equation. So this would be x squared plus 8x plus 17. And I know it's a quadratic because we started off with an x cubed. We divided out one of the x's. That leaves us with an x squared. Unfortunately, it does not factor. There are no factors of 17 that are going to add to 8. So we have to go to the quadratic formula. So we're going to use, again, they are not hard problems, but they are involved problems. So x equals the opposite of b, that's a -8. Plus or minus the square root of b squared, which would be 64, minus 4 times 1 times 17, all over 2 times 1. So that's a -8 plus or minus the square root of 4 times 17, which I'm guessing is a -68. Yeah. So I'm going to get 64 minus 68 on the inside of that thing, all over 2. So that's going to give us a -8. Plus or minus the square root of a -4 over 2. So again, order of operations is important here. Make sure you do it in the right order. So we're going to come in and take that -4 and make it a plus or minus 2i all over 2. And then everything divides by 2. So that'll give me a -4 plus or minus I. So again, I have to divide this 8, this 2, and this 2 all by 2. And we end up with -4 plus or minus I. Okay, so to make sure we all understand what's going on, The zeros are the -5 that we tried in the synthetic division that worked. And then I also have a -4 plus I and a -4 minus I. And those are the 3 zeros for this polynomial function. So they then also want me to write it in factored form. This drives me crazy. There's no point in this, but this author really likes factored form. So we're going to recreate the polynomial. So the -5 is coming from a factor of x plus 5. And I have to be careful here as I bring each of these into the factor with the x, I need to switch their sign. So that's going to be an x plus a 4 minus I, and x plus a 4 plus an I. So notice because it was a -4, that inside the parentheses it's both positive 4s. The only sign difference is on the I. And there it is in factored form. So you found your zeros and you factored it. And I'm hoping you can see that okay. That red doesn't show up very well. Okay, any comments or questions? The same thing as yesterday, you're just going a little step further and adding in the I's. That's why it's a nice section. Okay, let's do some more just for practice. Everybody's good?
Yes.
Yay! So example 4 is a 4th degree polynomial. It says f of x is equal to, I have 3x to the 4th plus 5x cubed plus 25x squared plus 45x minus 18. Making sure I wrote it correctly. Yep. Again, when you copy them down, make sure you copy them correctly. So, okay, so how many zeros do we have this time?
4.
4. So we know we're looking for 4 zeros. Okay, and then we need our P over Q. And again, these are the possible rational numbers. These are anything that does not involve a radical or an I. Okay, so for us, we're going to have plus or minus. I need numbers that go into 18. Can somebody give me the numbers that divide evenly into 18 in numerical order? Got a 1?
2, 3, 6, and 9, and 18.
Beautiful. And we're going to put that all over this time factors of 3, which are 1 and 3. And then I'm going to expand that list. So I'm pretty sure that the homework is not going to collect or accept it like that. We need to expand it out. So we have 1 over 1, which is 1. We have 1 over 3, which is a third. We have 2 over 1, which is 2. We have 2 over 3, which is 2/3. 3 over 3 is 1. It's already listed. 3 over 1 is 3. I need to get it in. 6 over 1. 6 over 3 is 2. Already got it. 9 over 1. 9 over 3 is 3. It's already listed. And then 18 over 1 is 18. So it's a list, but it's not an exhaustive list. And again, when I learned to do polynomials, there were no graphing calculators out there. So you literally had to try these numbers in the synthetic division process until you found one that worked. So there are a couple more theorems that we no longer do that help with it, but you still had to try them. Okay, the next step is to graph it. So you go graph it and then tell me what numbers I want to try. Go for the left one just because it's usually easier as a class. So graph that polynomial and then tell me what one we should try. Okay, that's really exaggerated, but that's what it looks like. Okay, so comparing my list to our graph, what number should I try first?
-2.
Beautiful. So we're going to try -2. So let's see, we have 3, 5, 25, 45, negative 18. So you go through and do the synthetic division. Be really careful, don't make sloppy mistakes, which is so easy to do. So I ended up with a coefficients of 3, -1, 27, and -9. Okay, and we have our proof that we have a 0. So now I need to try this next number, which is sitting over here on this side. It's definitely less than 1, so it's one of these fractions. It's either 1/3 or 2/3. Does anybody have a preference on which one we try first? No? Nobody? Again, it's
1/3.
really hard. Yeah, 1/3. Okay, let's try the 1/3. And again, I don't need to go back to the original. It's important that you work on the depressed equation. So I'm just going to pick up the coefficients I already have. Don't rewrite anything. You don't need to. Just pick up what you've already got. So we'll bring down our 3. Multiplying 1/3 times 3 is 1. That gives me a 0. Fine. 0 times 1/3 is 0. 1/3 of 27, sure enough, is 9. And that gives me my remainder of 0. So your 1/3 was a good guess. Woohoo. Okay, so these two make up the real zeros. We're going to pull the rest of the zeros from this remaining quadratic. Our quadratic is what? 3x squared plus 27, and I'm going to set that equal to 0. Okay, just to tie stuff in, the graph up here only crossed twice. That's why we're getting only 2 real zeros. We're going to see that the other 2 zeros that we need are going to be complex numbers, so they're going to come out of this. So we'll have 3x squared equals a -27. So x squared equals a -9. So x equals plus or minus the square root of a -9, which is 3i. Okay, woo! So we're done with the problem. We just now need to write all the answers out that they want. So the zeros are the -2, the 1/3, and the plus or minus 3i. So I'm actually going to write those separately because it's easier to go into the factors when you do that. So 3i and -3i. So then in factored form, f of x is going to be equal to x plus 2 from that -2. Here I'm going to do my little sneaky trick with that 1/3. I'm going to rewrite that as 3x minus 1. When you solve that, you'll get your 1/3, and that 3x is going to give us our coefficient back up top. So then we have an x minus 3i and an x plus 3i. And there's the factored form of the polynomial. So, okay. At some point, they should get kind of fun because you have a plan of attack. You know exactly what you're doing with them. 2 more, and we're going to call it good. The next 2 are picked on purpose just to be sneaky, but to tie stuff in that you've already seen. So, okay, so example 5. Says f of x is equal to x to the 3rd minus 8. Same directions, find the complex zeros, write it in factored form. Okay, so prior to this section, what you probably would have done, and we're going to use it because it's nice and quick, is you probably would have said x cubed equals 8, or x cubed minus 0 minus 8 equals 0, sorry. And then you would have cubed rooted both sides. So the cubed root of 8 is 2. That works, but that's only going to give you the real 0. If you were to graph that polynomial, which we can graph already using transformations, I don't need my calculator at all. I know it's the cubic function and it's been shifted down to -8. So it does something like this. Didn't need my calculator. Well, we already know that it's crossing over here at 2. So we now know that that's 2. So I'm just tying stuff together that you already knew. Well, how does that help me out? Well, I know that we need 3 zeros. I know that the possibility for zeros are factors of 8, but I already know that 2 is a 0. So I can skip straight to the synthetic division and use my 2. So the real 0 that we've already identified, we're going to use. And now we'll write our coefficients. There's no x squared, there's no x, so I need those placeholders of zeros. So we'll bring down our 1, 2, 2, 4, 4, 8, and 0. So sure enough, it is a 0, which we already knew, but we verified it. Okay, what's left is x squared plus 2x plus 4. There are no factors of 4 that add to 2. So I have to go to the quadratic formula. Now, a long time ago, you may have learned something which was called the difference of 2 cubes as a formula. It's a factoring formula, but you now no longer need that because you can always use synthetic division, and it's much quicker than trying to remember the formula. Okay, so now we're going to head to the quadratic formula. So back to the QF. So the opposite of b is a -2 plus or minus the square root of b squared. Well, 2 squared is 4. Minus 4 times 1 times 4. All over 2 times 1. So it's a -2 plus or minus the square root of 4 minus 16 all over 2. So that's going to give me a -2 plus or minus the square root of a -12 all over 2. Okay, what can I do with that square root of -12? Well, 12 is what? 4 times 3? And the square root of 4 is 2. So I can pull out a 2i, and we'll have a 3 left over on the inside, all over 2. And then finally, we can cancel all the 2's. So this 2, and this 2 will all cancel and leave us with -1 plus or minus I times the square root of 3. Whew. Okay. So our zeros were the 2 that we found to begin with, and then the ones we just found. So -1 plus I root 3 and -1 minus I root 3. That is a really awkward 0 to write. Okay, does everybody follow that in terms of mechanics and things that you already knew and letting the new stuff work for us? Okay, I'm not quite done with it, but I need to erase because I ran out of room. They want me to write this in factored form. So in factored form, we're going to work off of that line. The first factor would be x minus 2. Now, as I bring both of these guys down, sorry, I need to change their sign. So that's going to be x plus 1 minus I root 3 and x plus 1 plus I root 3. So, and there it is in factored form. That's just ugly. That's some of the ugliest looking stuff that we see in our class, but there it is. So the cubics that we worked on, oh, I don't know, first week of class, this would have been a much easier approach. So, okay, one more. Example 6. So example 6, same directions. We would find the complex zeros of f of x equals x to the 4th plus 13x squared plus 36. And then we're going to write it in factored form. So I picked this one for a couple of reasons. One of it is got missing terms again, so I just need to get you used to using those missing terms. How many zeros are we going to have when we're all done? 4 zeros. Our list of P over Q. What is our list of P over Q? So what divides evenly into 36? Somebody help me out.
1, 2, 3, 4.
Good.
6.
Yep.
12.
Oh, missed one. 9.
12.
12. what, 18 and 36?
36,
Again,
yeah.
the reason I knew we'd missed it is 6 squared is 36, so that meant at that point I had to start getting the pairs of factors. So
Uh,
at 12 it threw me. It's like, well, wait, 4 times 12 is not 36. So good job. That's a big list. I don't like big lists. Okay, then you're gonna go graph it. And I need you to go graph it because something really goofy is gonna happen on that graph. So go graph it. Hey, notice anything unusual about your graph?
Yeah, it doesn't show anything.
It doesn't show anything. That's exactly it. So 2 things could be happening here. Now, if it were the 1, 2, 3, 4, 6, 9, we would see it because our window is big enough to cover that. So it could be that I need to make my window bigger and go out to 12 or out to 18 or out to 36. The problem is that all 4 zeros are actually complex numbers on this example. So your standard window is going to show them to you if there are any zeros in our class. So there are no real zeros because I don't see them. Well, that's great. What the heck do we do now? Well, we're going to go back to chapter 1 and we're going to use substitution. Isn't this quadratic in form? Isn't the middle exponent half of the first? So this thing is actually factorable. So we're going to come in and use substitution. Substitution. And that was back in section 1.4, I think, where we started. Okay, so we're going to say that that is, sorry, let me not skip too many steps here. So we're going to take the x to the 4th plus the 13x squared plus 36, set it equal to 0. We're going to let u equal x squared so that this becomes u squared plus 13u plus 36 equal to 0. So notice I took it out of the function format altogether and put it back into stuff that we started with. So factors of 36 that add to 13. So I've got the lists up here. Don't 4 and 9 add to 13? So this factors into u plus 9 and u plus 4. So u equals a negative 9 and u equals a negative 4. And then you have to unsubstitute. So each of those u's is an x squared. So we're going to end up with x squared equal to negative 9 and x squared equal to negative 4. So then x equals plus or minus 3i and x equals plus or minus 2i. So the reason we're not seeing a graph is because it only graphs the real zeros. It's not going to graph those imaginary zeros. So there they are. Okay, so our zeros, of which we found 4, so we have 3i, negative 3i, 2i, and negative 2i. There's all 4 of them. And then in factored form, f of x would be equal to x minus 3i, x plus 3i, x minus 2i, and x plus 2i. And you're done. You found your zeros and you've written it in factored form, so you're good to go. Whoops. Don't drop your i's. I dropped my I. Don't do that. So 3i, negative 3i, 2i, and a negative 2i. And there it is. So you're going to have one of these on the homework that when you go to graph it, you're not going to see anything. That's your clue that you could have factored it by other means that we've already talked about. So, and that's all of the polynomial function stuff. So that's all the polynomials. So on Monday, we're going to backtrack to section 5.2 and 5.3 for Monday and Tuesday, and those are rational functions. So we'll switch gears on Monday. So it worked out really good with the 4-day week to get through all the polynomials. So I kind of liked it. So, any comments or questions?
Nope, I'm good.
I'm good.
Yay! Okay, you guys have a wonderful weekend. Don't forget you have stuff due on Saturday and a quiz due on Sunday. Looking ahead next week, we'll start our next discussion, and also a review to date, I think, is next week also. Yeah, we have a review to date, so you'll be dropping another one to Gmail to me. So, okay, have a good one. Enjoy it.
You too.
Thank
too.
you. too.
Bye.